Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection as usual. Today, again, a very biased theorem. So I like it a lot. I find it very surprising. It's called Bondi Theorem. It's part of combinatorics. And it's this idea or this observation that you sometimes can forget information without losing information, which is kind of a bit weird, but we'll see what it is. So Bondi Theorem, as I said, why it is so interesting in my opinion is because it's surprising. The proof itself is not very deep. So the proof itself is 2 pages long or something. So maybe you can be a little bit, you could streamline a little bit, maybe you get it down to 1 page. The point is a little bit that as soon as I tell you that it's true, and somebody told, of course, me that it's true, links are always in the description, remember, that as soon as you know that, then you can actually prove it yourself. It's not like a classification of finite simple groups or something, where the proof is just tremendous. It's very simple, a very simple observation, and then, of course, also a very powerful observation, because maybe it could be called Bondi's lemma in the sense that it looks very applicable, and you can use it in many combinatorial arguments and just counting certain things, and it's pretty nice. It's pretty nice, and it boils down to the following very simple observation. So here I have 2 cubes, about this, and the only thing I do, I choose 3 points on my 2 cubes. Okay, 3 points. So here's my point here. Here's the point, and on the other cube was kind of the same cube anyway. I'm just choosing three points on a cube. And I'm asking the question whether I can project down to, well, a square, so a 2-dimensional cube from 3 to 2, I can project down such that whatever I see is still different. So I'm chosen 3 distinct points here, 1, 2, 3, 1, 2, 3, and I'm asking, they live in 3 space, and I'm asking whether I can project to 2 space such that they're still different. So for example, if I would project on the blue plane in the front, this one goes to here, this one stays where it is, and this one goes to here, and they're still distinct, right? So this is not quite trivial. So in this case, I could also project to different planes, but here, for example, I could project to this one. But if I would project to the front plane, obviously those 2 would collide, so that's not good. So it's not quite trivial here that you can always find a projection plane, right? It's 1 dimension lower. It's really not quite clear. You lose information, but you can, such that all your 3 points are still different. So no matter where you choose your points, where you put your points, you will always find a plane, and you can project down, and you still have 3 different points. Right? That's exactly this idea of forgetting without loss. I forgot that I am 3 space, I just go down to 2 space, and I still have 3 different points, which is kind of strange. And now you play around with bigger hypercubes. Well, you can try it yourself if you want. But here, this is kind of really strange. So what we would, it looks like something is going on. Not quite yet, maybe it's a little bit too silly of an example, but well, there is a reason why I'm doing this video. So there's something going on anyway. Okay, here comes a more convincing example. I just use the 4x4 matrix. You can choose a bigger matrix if you want. And you again lose some information. You go to a 4x3 matrix or to a 3x4 matrix. That actually doesn't really matter so much. But you certainly lose one of them. You either remove a column or a row, and you could still have the following property. So here I have how many rows, 4 of them, right? And they're all different. So if you look at the rows, you will see that they're all different. 1, 1, 0, 1, and the next one, and the next one, and the next one, they're all different. And if you look here at the columns, you will realize that they're all different, right? So whatever, first column, second column, whatever, and we are in 4 space. And now we forget one of the coordinates. We just cut out 1 coordinate. Here's this one or this one, and whatever remains, oh, surprise, surprise, the vectors are still different. So here's only 1 vector. It's certainly not this one. It's certainly not this one. It's certainly not this one. And they're all pairwise distinct. And same here. This vector is not this vector. It's not this vector. It's not this vector. So same pattern, right? I restrict to a lower dimension, and I had how many distinct before, and I have the same number of distinct things afterwards, although I made my problem smaller. I forgot information. I forgot here that I have a 4x4 matrix, and it still works. And now you can try the same with your favorite 4x4 matrix, and it will still work, which is maybe now very convincing that something is going on here. Of course, you can try the same now with a 5x5 matrix or a 6x6 matrix or whatever, and it will always work. And that's already weird, isn't it? That's something I wouldn't have expected, right? It's kind of weird. And it's, again, non-trivial. So if you, for example, cut out the first one here, you would see that those two, for example, then collide, right? It's really not trivial. The only statement here is that there is something you can remove such that they remain distinct. Not that you can remove everything. That would be a little bit too much, I guess. And it continues. There's zillions of those examples. So 3 points in R3, and you can always project them down to a plane that they're still keep being distinct. It's exactly the same property, right? So just here, and you project down, and they're being distinct. And again, it's really the same type of observation here. So something definitely is going on, and that's exactly Bondi theorem. So this is how it looks like. Very innocent looking theorem, very powerful and very useful in combinatorics. So if you have a set with n distinct elements, this kind of the most basic version of it, just a set with n different elements. So let's say you have the set 1 to n, and you choose n distinct subsets, whatever, those. So the point is here n and n collide, then you can always restrict the subset to a smaller subset, n-1, and whatever you have chosen remains distinct, right? So this is this idea of forgetting information. You have n elements to play around with, you throw away one, and whatever you had before is still different. And that's kind of a really weird and surprising statement. I think that's really surprising, but it is true, and it's actually not so hard to prove. I tried to came up following a comment on mass overflow in the description with some reasoning why this is true without looking at the proof, obviously. So you can just follow the proof. It's not so hard. Link to the original papers in the description. The original paper is only 2 pages long. Very efficient proof. But anyway, how can that actually be true? Well, roughly, I would like to think about this as follows. So let's say we have n distinct vectors in Rn. So here 3 vectors, which are just points, obviously, in R3. Okay, so there you go, 3 points. And forgetting the east coordinate, that's what we do here, means something like there is a line orthogonal to the east coordinate vector between the 2 points that are then collide, right? So if they are identified after forgetting the east coordinate, and no projections distinguish those points now, it's the same that there are n pairwise orthogonal lines, namely one for E1 up to En, in my collection of points somewhere, and this just can't work because my endpoints certainly lie, here's an example, in an n-1. So this is a plane. So R2 and R3 and 2, they certainly lie in an n-1 dimensional subspace. So you can't have n pairwise orthogonal lines in your subspace. So in other words, they don't quite go along. This was kind of okay. If I explain it in this way, it might make sense why this works, but this is still so much more general that it still sounds so surprising. I think it's really surprising, like forgetting an element, and you could still have everything distinct, and because it's formulated in the set theoretical combinatorial language, you can just apply it to basically everything you want. So all of these examples were just an incarnation of the previous theorem. So that's very surprising in my opinion. And it turns out that the main point in the end was to try to generalize it. So here are several versions of the same theorem. So you can ask the following question. So here is a 4-dimensional hypercube. So how does it work? Well, you have a cube and you have this extra dimension, which is here a dotted line. So you have a cube and a cube. And if you think of how a cube works itself, so a cube is just a 1-dimensional lower cube connected by the extra dimension, and it's exactly the same here. So this is a 4-dimensional hypercube, and they are chosen 6 vertices along the hypercube, and you can ask, for example, the question, given a collection of distinct vertices, what is the largest d such that the projection gives a d cube? So here, if you project along the red, you get a d cube, as you can see, for d equals 2. So it's just, well, this one here goes to here, for example, this just collides to here, this just collides to here. So you just get here this little d equals 2 cube, which is just a square. So this is just an idea, and then you could ask this question, and that actually has a nice name. It has a nice name. It's called the VC dimension of the problem, and you can vary that a lot. And it's extremely important in various concepts in combinatorics and machine learning. So it's kind of the same type of question, generalizing this idea of Bondi, and you can actually get a measurement of how important or how deep your choice of points was in this deep, in the sense of what kind of subspace you get from them. Like really in the same flavor as this one here, I got a n-1 dimensional subspace, and you might ask a very similar question varying the number of points. So the restriction here is that I always have n and n points. You don't need to do that. So here I had n equals 4, and I've chosen 6 points. So 6 points, right? So that's not the same, and you can vary the question a lot. And you get some very interesting combinatorics, always based on this idea, this pretty crazy observation actually of Bondi theorem. So Bondi theorem, I mean, I find it still surprising. In particular, if you think about the matrix picture, I find the matrix picture very, very surprising. So you take your n by n matrix, cross out, and it has distinct rows and columns, or just let's say rows, and cross out one column, then usually they should collide, and not all row vectors should be different anymore, but you can always find a column such that they are still different. So you lose information, you make the matrix smaller, and they're still different, which is kind of a really strange result. But it's true. It's basically a counting argument. So link to the original proofs in the description. Anyway, I hope you enjoyed the video, and I also hope to see you next time.